Hi, this is Group 8's video project for Mech 300. The project is over a heat exchanger, which is a part of the slingshot. We'll be using the Fundamentals of Engineering Thermodynamics, 8th edition by Wiley to help with this video. Shown here is a simplified version of the slingshot, which is a water purification device made by Dean Kamen. We'll be focusing on the heat exchanger. Heat exchangers are useful because they allow heat to pass between fluids without the fluids ever coming into contact with each other. An example heat exchanger problem is prepared in the next slide. For this problem, what we're given is the table and diagram of the heat exchanger. We know the pressure for states 4 and 5, the temperatures for states 1, 2, and 5, and the quality of the state 4, which is 0.95. The system is open at steady state and with no heat transfer. Neglect the kinetic and potential energies. We will approximate the H values for states 1, 2, and 5 as HF, since this is liquid water, and will give a close approximation. Problem A asks us to find the ratio of the mass flow rates of m.1 over m.4. Looking at the diagram, we can see that mass flow 1 and mass flow rate of 2 are equal, and also that mass flow rate at state 4 and mass flow rate at state 5 are equal. Shown below is the entire energy balance. Since this is a steady state energy balance, and taking our model into account, the kinetic, potential, work, and heat terms all drop out, leaving us with 0 equals m.1 times h1 minus h2 plus m.4 times h4 minus h5. We can rearrange this to get m.1 over m.4 equals h4 minus h5 over h2 minus h1, which is what we're trying to get. Now we just need to find the h values. Following our engineering model, we will approximate the h values at states 1, 2, and 5 with HF, using tables A2 and A3 in the book. The results are shown in the table below, which are here, here, and here. Now we need to find H4. We can look in table A3 at 0.1 bar and find the HF and HG values. Knowing that the quality is 0.95, we can find H4 as HF4 plus X times HG4 minus HF4, and get H4 as 2465.1 kilojoules per kilogram. Now we can solve the m.1 over m.4 equation we found earlier. Solving this, we get 36.3, which would seem to me very high for a water purification system, but this is just an example. For part B, we need to find the energy transfer from the steam to the cooling water in kilojoules per kilogram of steam, which is Q dot over m.4 equals H5 minus H4. We already have everything we need for this problem, so we just plug in the H values and get Q dot over m.4 equals negative 2276.7 kilojoules per kilogram. The negative meaning that the energy goes from the steam to the cooling water. Alright, that's everything. Thanks for watching.